All right, welcome back everybody. Today we're going to continue working in R a little bit. We're going to go from where we are now up to when we start, right before we start looking for differentially expressed genes. So today we're just going to get some plots that will give us indication as to whether or not we should expect some differentially expressed genes when we start looking at DSeq2. The first thing that we can do is in here, we're just going to do false equals and then capital false, and then true equals capital true. We're going to set these variables. They make it easier later on when we need to type in true or false. In my opinion, I'm not one for the needing it to be caps. Even in Python, they just have the first one capital and then like for true, lowercase R-U-E. It's just faster to type. Caps make it a little bit slower, but here we're going to add in eval equals false, and then we're going to do the same thing with this block. And what this is going to do is it's going to tell R that when we knit this, we don't want it to run these blocks. So down here we can get just an example. We can do head of count data. We can run it. We knit. Should make a really nice HTML file. There we go. We have all these extra things too. Now when we load in the packages, we can mute that by doing message equals false, and then we can knit again. And it should be much cleaner. There we go. So it still prints these out. So we have our code in here, and then we get our table, just the first 6 rows of our table. Good deal. We're going to add a couple of these R blocks down here. Okay. If we look at our count data, we can see that we have 13 columns, of which our gene ID is the first one, and the next 12 are going to be our samples. But when we start analyzing the data, we don't want our gene ID in here, because then we have to parse out the second column through the 13th column instead of just saying our count data. And that's pretty easy to do. If we do down here row names of our count data, so we want our count data row names to equal what we feed in, and that's going to be count data. And then $sign is going to give us a list of all of our columns and gene ID. So we just run that with Control Enter, and we look at our count data now. We see that we assigned all of our row names. So our row names equal to our count data table, column, gene ID. So now these two are equal. With that first column now being assigned to our row names, we no longer need it. So we can do count data equals count data. And then within the brackets, we put a comma. Before the comma is going to be rows, and after the comma, it's going to be columns. So if down here we look at count data 1 and 1. What that's going to do is find count data. It's going to look for the first row and the first column. It's going to pull in this. And you can see that here. If we want to remove a column or a row, we can put minus in front of it. In this case, to remove that first column of gene ID, we can go to the column side of the comma and then press -1. Run it, and then if we check out our count data, we removed that first gene ID column. All right. Now to make it downstream processing of the data a little bit easier to do, we can parse out names. Here, when we renamed them in Excel, we just gave them their group name. So in this case, we just gave it p53- and then mock for the first 2. But R knows that you can't have 2 columns with the same name, so it puts a 1 at the end of it. Let's rename them. That way we have the group and then the replication all together. So I'm just going to copy this one over, paste. So now we have our new columns. We're going to call this columns, and then we're going to label our count data columns as that. But we have p53 minus mock, so that's what we just what we gave it in Excel, but this time we're giving it this _1. And we'll be able to pull out the group later with a function. Now let's name the column headings that. So just like we did with the row names, we can do col names of our count data. And we can set that equal to our columns. Let's take a look. There we go. We have our newly named columns that follow a little bit better naming scheme for R that includes the replications. Let's do a summary here quick of the data. So summary of our count data. We can see the minimum is 0, the first quartile is 0, median and mean are vastly different, but we have some that go really far up. Let's do call sums of our count data. Here we see that we have a wide range of what we call library sizes of the different counts for each column here. So each column is a different sample, but we can see that here p53 positive Mach 1 has more than twice the number of reads that TRP53 positive irradiated 2 has. And later on, DSeq is going to have to take that into account when calculating differential genes, because if in p53 positive Mach rep 1, there's 50 reads that show up here and only 25 show up in this positive irradiated rep 2. If we're just looking at raw numbers, sure, it looks like in p53 positive Mach 1, there's something happening that's causing twice as many of those reads, when in reality, if we divide it by the total number, that's total number of counts in that file or in that sample, we see that they're not that different. If this has 50 and this has 25, they're not as different as the raw numbers may seem. So let's get a better visual of what this looks like. If we do bar plot of those call sums that we just did, so call sums of our count data. Let's add in our labels. Let's do some margin stuff. So we'll increase the margins, that way we can see our actual names. 8441 plus 0.1. See how that looks. There we go. That's kind of hard to interpret. There we go. So now we see that TRP53 positive Mach 1 has more than 80 million total read counts in that file, whereas the TRP53 positive irradiated 2 has maybe 40, or we saw before 41 million reads. So just something to note, DSeq is going to have to internally normalize all of those counts. Let's look at within each file. We see that we have a lot, or in each sample, we see that we have a lot of zeros, a really low number. Well, this is log count. We're going to make log count. We have a lot of zeros here. Looks like the majority of them are actually 0. And that we saw too up here with the summary. We can see all the way up to 25% of the number of samples have 0 in there. So let's visualize that. And we can do that pretty easily just by doing a histogram. We can do a histogram of our count data. We can look at that first column. And then we have to do BR. So this is going to split the number. So if we have 0 counts on the left-hand side and 28 million on the right-hand side, it's going to split it up into however many bins we put here. So if we put 100 bins and we plot this, you can see that most of them are staying around that 0 mark, which can make it hard to work with. A way to fix this, and a lot of times you'll see or hear of people talking about how they transform their data. Here we'll do what's called a log base 2 transform. So basically we're going to look at how many times a particular number can be halved divided by 2. So if we do 2 log base 2 of 2, we'll get 1. If we do log base 2 of 4, we can divide that twice, so on and so forth. 8, 16, all the way up to 32, just as an example, 5. So it's basically figuring out how many times that number can be halved. So it's going to bring those really high numbers. We see we have 28 million here. If we do log base 2 of that, we get a number very, very different. But since we're treating all the data the same, it's appropriate. And to do that, we can do create that table called log count data equals log 2, and then we have to add this 1 in, because if we take the log of 0, we get negative infinity. So we have to add a log. We have to add a number before we log transform it. If we do our count data, it'll make it look much nicer, and we can see that by going here. So we pulled all those really high ones down to about 11. We got some 13s in here, but all the zeros stayed 0. And there was a 1 in here somewhere. Log 2 of 2. It's 1. So that would be this guy in our count data. All right, let's visualize this one now. So we'll do a histogram of our log count data. We'll just do that first column again, and we'll do the same 100 bins. There we go. Now we can start seeing that not all of our samples are actually 0, which we know. And then I pulled those really high ones down. That 28 million is now 25, 24, like we had seen, 24.7. We have more squished here. And the distribution, not ideal, but it's much better than very, very skewed. So if we look at the x-axis, like I said, we pulled all of those down to be more comparable. But now, like we had seen with the IDEP, let's plot some replicates against each other. So we would expect that perfect 45-degree angle if they are similar or if they're identical. We do plot or log count data. We'll plot the first column, and then we'll do log count data. We'll plot the second column. And it seems pretty similar. If in an ideal world, perfect replicates, so if we plot the same thing against each other, we'll see that perfect 45-degree angle. That would mean that there's absolutely 0 biological difference in the gene expression between these two samples. That doesn't happen in biology, obviously, but that would be a perfect world. Here we can see that correlation is pretty strong. If we want to look at a sample against a different treatment, so 1 and 3, that would be TRPV3 minus, then mock, and then TRPV3 minus, and irradiated. If we look at that, we can see that that's not as correlated as the individual replicates. We can also look at 3 and 4 to make sure that this isn't happening just because 3 is an odd one. So if we put this as 4 and this one as 3, and then run it. Yep, so 3 and 4 are similar to each other, 1 and 2 are similar to each other, and then 1 and 3 are more different. So the radiation that was applied to this mouse caused something in the p53 minus mice. All right, we're going to add a couple more here. All right. With those kind of out of the way, what we can do now is start designing our treatment information and our metadata, if you will, of the mouse or of the different samples. So for instance, we have TA53 plus and minus, so we can make a column that has just P53, whether or not it's positive or negative for that gene. And then we can also have another column for the treatment of that mouse. So was that mouse just a control mouse, or was that mouse irradiated with radiation? I'm just going to copy this over. Run that. So now we have P53. We're supposed to. There we go. We have P53 with our minus, 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 and then the rest are positive. And then we have treatment. So we have control, control, irradiated, irradiated, and then control, control, so on and so forth. We're going to make a another table. We'll call it call data. And we're going to set it equal to make a data frame as data.frame. We're going to column bind and then set the first column of our new data frame of call data as the call names of count data. And then after that, we want the next column to be P53, and then the next column to be the treatment. So we'll have the first column as the column names, second column as MMMMM, PPV, so on and so forth. Treatment will be control, control, irradiated, irradiated. We can see that if we do call data here. Run all of it, and there we go. We have our table, which we can then feed into DSeq2 in order to build our DSeq2 object. So the function that we're going to use, if we do question mark, we'll do DSeq data from matrix. You see over here, we'll need our count data, our call data, and then a design. So any of them that doesn't have a equals false or equals null afterwards are generally required. And here, see if they give an example too. Yep. So a lot of times they'll just use DDS. So we'll use DDS and then DSeq data from matrix. And it's always a good habit to put in exactly what you're doing. So we're going to set our count data equal to our count data, even though it's not required, because DSeq knows that the first one is going to be our count data. The second one is going to be our call data. And then it's going to be the same name. And then the last one is going to be design. So for the design, we have to kind of specify exactly what we want the experiment to have involved. So we have our P53 column, and then we have our treatment column. So this is, if we run this and we want to look at later just the differences between the P53, so we can see whether or not P53 minus and P53 plus, if there's difference between these 4 and these 8. Additionally, here we have treatment, so we have the ability later on to see the difference between controls and irradiated. But in our case, the more important thing is there going to be any interaction between P53 and treatment? So we have to do times treatment. Because it wouldn't make much sense to compare P53 minus to positive, because some of those samples were control and some of them were irradiated. And then it wouldn't make any sense to do just treatment if we want to look at the control versus irradiated, because their different expression profiles. So some of them have p53 and some have that knocked out. So this interaction is there any difference between p53 and treatment that would then be amplified by having p53, a particular p53 and a particular treatment, which is exactly what we want to look at. And then we have to convert that. So this is creating the DSeq data set. We need to convert that into a DSeq object. So we're going to take that DDS and we're going to convert it with just DSeq, and we'll put DDS inside. So we run this. It'll take a little bit. Sometimes it takes a lot of it, depending on how big your data frame is. And then we can look at the number of rows that are in our DDS object. And we expect, like we see here, there to be the same number of rows or same number of genes that it is there that is present in our original file. Additionally, there are ways to filter out. So if you don't want to look at all of the zeros, we can set a threshold there. So generally, if there's zeros somewhere, it's not always the case. Like in here, we have 1. But we can filter this out a little bit if we want to do, say, less than, we don't want it to be too big, but less than 3. So if a row has a count that's less than 3, we'll just take that row out, or we can do 5. So in this case, there's 5. If it's less than 5, this one would be kept, but like in this case, this row would be gotten rid of. It'll just eliminate, so we have 4 reps. If there's a 1 here, but the other ones have 0, it might not be that pertinent. So we'll do DDS and then row sums. So instead of like before we were looking at call sums, we'll look at row sums. So between all of the different samples for a particular gene of DDS, we want those to be greater than 5. We need counts of DDS. There we go. And then we can do the number of rows here and see how many we have left. So now, all of those, out of all of our genes that we had, we only have 21,856 of them that had a row sum of greater than 5. So we eliminated a lot of very low counting genes. The next thing we can look at, like I mentioned before, is going to be that size factor. So size factors of DDS. We can see that it knows now, DSeq knows that TR53 positive Mach 1. We're going to copy this and paste this down here, and then it'll show up on the right-hand side. DSeq2 knows that TR53 irradiated minus irradiated 2, so this guy, and p53 positive Mach 1, this guy, have much more reads in it than like p53 positive irradiated 2, that would be this guy. So DSeq2 now knows that there's some normalization that has to take place based on these size factors. Let's look at a principal component plot. So we'll do library ggplot2, and then we'll calculate the regularized logarithmic transformation. So our log, the log 2 scale. So RLD is going to equal our log. We want it to be of our log of our DDS object. So we're just going to take into account the ones that we have left, the genes that we have left, and not all 31,616. And then sometimes takes a little bit. we can plot the PCA of RLD. So what this is going to do is it's going to find, out of the high dimensional data, two possible axes. So if you draw a line through your samples, if you plot them in that high dimensional space, which ones would explain the most variance between your samples. And then we can look at an int group. So we can either look at which would be P53. So do we want to look at just gotta run this guy. PCA, not PCR. So now we have our group for P53 minus and positive. So these over here are minus and these are positive. We can also do treatment. So you can see these over here on the left-hand side are controls, and then spread out here are irradiated. But for us, it makes more sense to plot the combination of the two. So we'll plot P53 and our treatments merged together. There we go. So we see that P53 controls are still over here, and then your irradiated are over here. And then we can see that our minus for both can be split by a line here, and positive is over here. Something that is interesting is that our P53 positive irradiated is way over here, and our positive control is kind of clustered over with the other control. So P53 is doing something to this expression profile to push it way away from the controls, and even so away from the minus. So that would be a P53 cause. So there might be a lot of genes that P53 impacts based on radiation. So P53 didn't have any impact on downstream gene expression, and we were only looking at radiation, then we would be able to see these here. So the positive radiation, P53 positive, should be close to minus irradiation if P53 had nothing to do with the radiation damage in mice. Like I had mentioned before, now we have to, we can plot a heat map, and to do that we'll need two different functions, actually 3 different functions, but 2 of them that will be really helpful for the third. We can do detect groups, and I'm just going to copy this in. What this is going to do is it's going to look at our call names, so call names of our count data. It's going to look at this, and it's going to tell us which group these belong to. So if we put parenthesis at the end and do detect groups, you can see that it knows now that this first 2 are from the same group, second 2 are from another group, and the next 4 are from the P53 positive mock, and then following that is positive irradiated. Then we'll look at a distribution function, or a distance function. So we'll add that in here. There we go. Oh, there we go. Now on the right hand side we have our 2 functions. The distance function is going to calculate how similar a particular gene is in P53 positive irradiated compared to the other ones here. So this expression of a particular gene is probably going to be a lot more similar than the expression of P53 positive irradiated to P53 positive control. So it's going to calculate the distance between all of those and then we'll be able to plot like the heat map to show how similar a particular replicate is to another replicate or even a treatment. Now we can do our heat map. So library, we'll use gplots for this. All right. That other function was hclust, which is this guy. Solve that by doing that. So now we have three functions. We have detect groups, distance, and hclust. And then after that, we'll set the number of genes that we want to look at to 100. We can do 52. So this will be the top genes that we're going to look at. X is going to be the data frame that we're working with. So we're going to make RLD, so that regularized log transformation that we made from the DSeq to the DSeq object. So it's log transformed, like our log count data. Then we'll have, I'm just going to copy the rest of this. So this is all on the GitHub page. So basically it's just going to calculate how similar a gene is, within a treatment and then between treatments for all of the genes. So if this one is more similar to, say, p53 positive Mach4 than it is to irradiated, well, like we can see way over here, irradiated positive, it's going to cluster it closer to that sample. We go ahead and run this. We get a little error for figure margins, but that's okay. So here's the top 50 genes, and we can see that radiation of the mice does cause a very large difference in gene expression compared to the other samples. Here we have Mach that has p53, but not irradiated. And then over here we have p53 minus irradiated and p53 minus Mach. So the lack of p53 is also causing something, whether or not the mice were irradiated or not. And that could be something like an apoptosis, downstream cell death signaling that it just can't control anymore, or lack thereof. Whereas here seems pretty mild, down expressed in comparison to over here, where there's a lot of genes that are being upregulated from the radiation while p53 is present there. So now that we have indication that there is some difference between the different sample groups that we have, or the different treatments that we have, based on all these plots, the next video is going to be talking about how are we going to tell which genes are different. And then we can look at, okay, these genes are different. What does that mean for like pathway analysis or Go enrichment? Is there a biological impact? Is there some metabolism difference happening? Gene ontology stuff. But yeah, so this is a good step in the right direction, that we can see positive, p53 positive mice are in fact acting different, or have different expression profiles in their transcriptome than the other ones. So hopefully we get some really good gene differences here. So I think that's gonna do it for today. Next time we'll, like I mentioned, break down the data and start going through DSeq, DSeq2, and calculating the differential gene expression. So yeah, see you next time.